Now we will start with this obtained spectrum. You will, by this response function, you will obtain a convolution of this observed spectrum, and this response function, you will obtain a spectrum which is produced by this detector, and you will obtain this analog signal, but it is digitalized and transferred to converted to spectrum in computer. That means we will obtain channels with the constant width. Yeah, and that means we will have this different channels, and from energies it is transferred to channels. Whole spectrum and also this response function, it's possible to divide to two parts. One part is this absorption of all energies. That means it's this part which is in this full absorption peak or also photopeak. Yeah, that means in reality it looks like approximately as Gaussian. And the second part, this is which is produced by this incomplete energy conversion. That means this is background which is produced by this Compton edges, Compton continuum, by this different parts of this spectra. That means, we have no only monoenergetic spectra, but we have many lines. We have some discrete spectrum of some monoenergetic lines. And in this case, this measured spectrum, again, it will be from these parts which are given by this full absorption peaks, and also these parts which are given by the continuous background. After there are the spectra which are depend on energy, and after digitalization we will obtain the same in the channels. But again, it is possible to distribute to these monoenergetic lines, this full peaks, full absorption peaks, and continuums. That means it's necessary to analyze full absorption peaks for determination of intensities, and on the this background of continuous background which are produced by this Compton scattering. This full absorption peaks, the best as is possible to approximate is Gauss curve, and that it is possible to neglect the natural line width, which is given by this lifetime of this excited states, and it's necessary to say that this lifetime is relatively long, and that means this uncertainty of energy is very, very small, which is given by Heisenberg principle of uncertainty. Here this is this Gaussian, which is possible to use for description of this curve. It is necessary to say that we have also a special situation, which is, for example, for X-rays. In this case, this curve is a little different, and it's necessary to use Lorentz curve or in reality convolution of Gaussian and Lorentz curves. This is this Lorentz curve, and on the end, in principle, it's necessary to have some convolution of this 2. Background is approximately possible to describe by linear or quadratic function or higher polynomial function, and you will obtain this description. Okay, you will obtain areas of these Gaussian peaks, and also you will have position. This area is important for determination of intensity, and energy is necessary to, this position is necessary to know for derivation of energy. To obtain a calibration of energy, that means which channel is which energy. For this, it's possible to use, or it's necessary to use calibration lines, some etalons or standards. And the primary standard in this case for gamma range of electromagnetic waves is a line of radionuclide gold 198 with energy 411.8 keV. Yeah. Here, this is this with accuracy, and it's necessary. Here is conversion to wavelength. That means this is wavelength of this radiation, and it's necessary to say that this is absolute calibration. That means it is calibration against, and accuracy, how it is calibrated against, for example, visible electromagnetic waves or against this radio waves and this another wavelength ranges for electromagnetic radiation. In reality, it's possible to obtain relative accuracy even better than in this case. That means it is approximately 1 electron volts, but it's possible to obtain even better. But this absolute calibration against this another ranges of electromagnetic waves is much complicated. Okay, this is primary standard, but we have some another primary calibration sources which are connected and which are calibrated and normalized on this line, and we have measurements with very high accuracy. Yeah, this is radionuclides, for example, 192 iridium, 169 ytterbium, and 170 thulium. Yeah, and how we will obtain this energy calibration? The best is possibility to make common measurements of calibration and measured sources. Yeah, that means, for example, if we need to calibrate energy of lines for yttrium, for example, that means we will measure this radionuclide of yttrium together, for example, with this ytterbium 169. Yeah. Okay. Sometimes it's possible to use if you have accurate energy for gamma lines in decay scheme, yeah, and cascade. In cascade, it's possible if you have the parallel decay by 1 gamma and 2 gammas. It's possible to obtain information of this energy of some gammas with higher energy, which is the sum of these two gammas which are in cascade. That means it's possible to use cascade in decay scheme to obtain information about energies and to use for calibration. Okay, that in this case it's possible to do some scale and relation between energy and position in channels, and it's this function usually because it is oftenly working in this way that should be near to linear, but okay, quadratic it's sometimes better, and okay, in any case this is not a big polynomial which is necessary. Mostly this these electric devices which converted this energy to the spectra in channels are very near to linear. Second necessity, you need to know intensity of gamma detected gamma radiation, and for this it's necessary to know detector efficiency. It's necessary to determine efficiency of detector. There are two efficiencies different. The most important is efficiency to full absorption peak. That means detection in full absorption peak. This is named as epsilon F, that means photopeak. And second, it's total efficiency. That means this is probability that this gamma will be possible to see in spectra in this full absorption peak. For total efficiency, this is probability that this gamma will be detected in any position of spectra. That means also this is this continuum, Compton continuum, in any part of this response function. We have also quantity, which is spectrum purity, and this is ratio between number of photopeak gammas detected and number of total registered photon. Yeah. That means it is ratio between efficiency of photopeak and total efficiency. That means relation between photopeak efficiency and the total detection efficiency is given by this relation, where this R is spectrum purity. Again, this is necessary to measure this efficiency by calibrated sources, which you obtain from special laboratories, which are also centers for production of such calibration sources. And as usual, calibration sources are used this europium for 152, for example, cobalt 60, yttrium 88, cesium 137, and europium 154, cobalt 57. In this case, this is, for example, radionuclides with one gamma line. For yttrium 88, there are two gamma lines. For cobalt, also two gamma lines. Europium 152, if you remember, there are many gamma lines. That means it is nice to see whole efficiency in whole energy range, and okay, that means it's possible to use for calibration. Here is some example where these radionuclides and calibration sources were used, and it's possible to see that this efficiency, this is this full absorption peak efficiency, and that this efficiency is approximately about few percent. That means for germanium detector, this is one of our germanium detectors, and here it's possible to see this efficiency measured by these calibration sources. For description, which is possible to see, it is possible to use this log function here, and this efficiency, logarithmus of this efficiency is function of logarithmus of energy. Yeah, here you see that you have also logarithmic scale. Okay. There are also one possibility how is possible to measure absolute activity. Yeah. That means in this, for example, if you want to obtain this calibration source, which is possible after that used for efficiency measurement of different detectors. In this case, it is fine and it is necessary to have calibration source or radionuclide which emit one electron, that means one beta, this is beta source, and after that one gamma. And it's necessary to be that conversion coefficient is negligible because if it will be not negligible, you have new electrons, not only from beta decay. And it's necessary to have one detector which is only which detects only electrons. For example, in this case, it's possible to have this gas detector. Second detector should be only detector of gamma. This is possible to do also in this way, that here you have you will have some absorption foil which absorb this electron but not this gamma. Okay, fine. And if you will make measurements with such system, this number of detected electrons will be given by activity, because any decay will produce one electron and one gamma, and times efficiency of this detector to electrons. Yeah. Second equation we have this number of detected photon will be given by activity again, because any decay will produce one gamma, and efficiency of this gamma detector, which is here. Here is scintillation detectors, natrium iodide, and here is electron detector, for example, some gas counter. And also, if we will put here coincidences, it's possible to calculate number of coincidences in this way, because this probability of detection of electron and probability of detection of gamma are independent quantities, independent probabilities. Whole probability is given by multiplying of one probability by second probability. That means number of coincidences which we obtain here are given by activity times probability of detection beta and probability of detection gamma. That means efficiency of detector beta, electron detector, and efficiency of this gamma detector. That means we will obtain this. Okay, have a look on it. If you will multiply this, yeah, and beta and gamma, yeah, you will obtain a square epsilon beta times epsilon gamma. And okay, that means it's after that it's possible to divide this multiplying by this NC, yeah, and because here will be epsilon beta times epsilon gamma divided by epsilon beta, epsilon gamma is 1, and will be a squared divided by a is a. You will obtain a. On this side, you will obtain this. That means you will obtain activity, absolute value of activity of this radionuclide, and after the termination of this activity, it's possible to use this source as source of detector. Okay, one thing which is necessary to do, there are different corrections of spectra and different corrections of our measurement. One correction is given by this because in any case, if you have detector and you have your source is not a point-like source usually. You have some foil or you have some body which have some sizes, and also this accuracy of determination of this distance of this detector to of this source to detector, it is different. That means it is necessary to know uncertainty of this source position and thickness of this foil. Yeah. This is really a simple thing which is possible to obtain from geometry, and here is some examples which show you how it looks like this relative uncertainty which is given by this thickness. And here, for example, you have, if you have foil which have 1 millimeter or 2 millimeters, and okay, that and also if it is approximation or if it is accurately, and you see that it is within the range a few percent, this difference. Second correction, which is necessary also to use, it is a self-absorption correction. You have situation, for example, if you will have some more thick foil, that also this gamma, and okay, these foils were irradiated, these radionuclides were produced, and you have homogeneous distribution of these radionuclides inside this foil. That means that if you have this foil in some distance of detector, that means that you have some gammas which are going through the whole thickness of this foil before running to detector. That means if you have situation that energy of this gamma is small, that means cross-section of photo effect is high, is a big probability that will be absorption during. Yeah, that means this gamma intensity decreasing by absorption, and this decreasing is given by this thickness of this foil. If you have this source with homogeneous distribution of radionuclides and some thickness, it's necessary to do integration, because you have some of gammas which are going through whole thickness and some which are even on opposite side of this foil near to detector, and you will have zero thickness of material which is through which this gamma is going. That means you have integration from x0 to this d, and you have this dependency of this gamma on this thickness, yeah, and you have integral. It's necessary to integrate, and you have this limits of this, and you will obtain this result. That means from this you have correction coefficients, which is given by ratio, but by this intensity of gamma, which are irradiated, and this is this gamma which are measured, which are running to detector, and this ratio is given by this material constant, this absorption coefficients and thickness of this foil. They are also necessary to do corrections which are based on coincidences. I already said you something about pileup and these things, and okay, that this is necessary to correct on this, but we will discuss this during our exercises. That means we already discussed interactions which are necessary for description of interaction of gamma radiation with the matter. That means about photo effect, Compton scattering, pair production. Yeah, we discussed how looks like the spectrum which is produced by this interaction in detectors. Yeah, and also we discussed how is possible to analyze obtain spectrum, and how is possible to obtain information about intensity of this gamma and energies of this gamma lines. Now we will discuss which detectors are possible to use for detection of gammas. At first, we will discuss which quantities are the best for description of characteristic of detectors, and for which it's necessary to look to manuals if you want to buy some new detector for your experiment, for your analysis. Yeah, that means, okay, we will discuss these characteristics. After that, we will start to discuss different type of detectors which are used for detection of gamma. Firstly, it will be scintillation detectors. After that, semiconductor detectors, and we will also discuss this crystal diffraction spectrometers. Yeah. Okay, here we have some examples. This is, for example, BGO crystals, which are scintillation detectors, which are used for detection of gamma. Here, how it looks like some detector of which use this natrium ionide. That means, again, this is scintillation detectors, which are, for example, used on satellite Fermi. Here you have germanium semiconductor detectors, and here they are spectra, and this is important. Yeah, it is possible to see that for detection of gamma, plastic scintillators are not fine, are not possible to use because this is very small probability of photo effect, and also from this reason, this resolution of this plastic for gammas and efficiency are very, very bad. The best are this scintillation detector, which are based on higher, heavier elements, which are much better because if you remember, this increasing of cross-section of photo effect is with Z in 5. That means it is very strong dependency on proton number. Resolution of these scintillation detectors are much better than this plastic. On plastic you will see nothing, but this is much worse than it is resolution for semiconductor detector. This is example of spectra from high purity germanium detector, which is excellent, which has excellent resolution for gamma detection and for energy. Okay, let's have a look on these characteristics of detector. First is sensitivity. This is capability to produce measurable signal for a given type of particle and energy, because we have some detectors which are sensitive for one type of of particles and for another type of particles. For example, we have detectors which are very sensitive for charged particles, and they are not sensitive for neutral particles, and we have some which are sensitive for electrons and not for gammas, and in opposite we have also which are sensitive for gammas and not for electron. This sensitivity depends on cross-section of ionization reactions, and also in the case of gammas also on this photon reaction. That means this depends on cross-section of photo effect, of Compton scattering, and of pair production. If these cross-sections are higher, this sensitivity will be higher. They are also depending on detector mass and on construction, how this detector is constructed. If this volume, sensitive volume, will be larger, the sensitivity usually is larger. In opposite side are working another two characteristics. Detector noise. If detector noise will be large, in this case, this sensitivity will be smaller. If noise is big, we will lose particles in this noise. And also, if thickness and material which will be around this sensitive volume of detector will be big, this thickness, and will be high level of absorption in this material, the sensitivity of detector will be smaller. Second quantity is response. This is the relation between particle energy and detector output. That means it will show you a connection between energy of particle and channel in your spectrum which you obtained in this detector. That depends on total charge or current amplitude of pulse which is produced by energy of particle. You have also response function. We already discussed this response function. This is function which you will obtain from a spectrum of monoenergetic gamma beam, in this case, this gamma detector. And this response function is based on the relation between Compton cross sections and this photo effect cross sections and pair production cross sections. Usually it is near to Gauss function with tail to lower energies, or with some function which describes this Compton continuum and these things. We already discussed this distribution which you obtained after conversion and digitalization of your spectra, and this is given by this spectrum and times this response function. Convolution of this spectrum and this response function. We also Sometimes it's important, mostly for detectors which are used for time detection. It is also time response, because this detector needs some time for signal creation. Yeah, and also it will be different pulse form of this time response. That means it is detector signal shape and how it looks like, this leading edge, declining. Yeah, and sometimes we have also more components of this shape. It is possible to see here. It is some example for barium fluoride, and this barium fluorides, this is scintillation detectors, and this response, this light production, have two components. One common component is narrow. It is about 70 nanoseconds, yeah, only. And second component is this long component and long tile. It is about 1 microseconds. Yeah, and the ratio between these two components is depending on ionization, and they are different for ionization from, for example, from different type of ions or from electrons, and ionization from gammas. Yeah, that's not ionization, but gammas is producing these electrons, and after that you have ionization, and on this ionization also this shape of this signal is depending. And it is possible to use this pulse shape for dividing of different types of detector. Next quantity is dead time. This is time which is needed for creation and analysis of detector signal. And there are two different types of the detectors. One type of detector is not sensitive in the time in which you have this analysis and creation signal and analysis. Second type is in this case in which your detector is sensitive during this work. In the first case will be not possible pile up, because you will have only this energy of this gamma which was detected firstly. For second type of detector, in this case you will have pile up. That means you will obtain sum of energies of two gammas which were detected in this dead time. Yeah. There are also two type of detectors. One which is described as case one. This dead time is not extended by detection of another gamma. Yeah, this is here. Yeah, okay. You have here signal. Okay, fine. That here you have second signal. You have also here signal, but it is not detected, and also it will not extend this. And you have signal here, again here also, and these two were not detected, and they have also you have not extension of this dead time. And here is prolongation. In this case, here is detection, and here is first, second, that means it is prolongation, and again, that means it will be in dead time detected also in the third, and okay, that you will detect only one from these three. Here you will detect two from these three, yeah, and here also this is extension, and end of this dead time is only here, yeah. Okay, this extension. That means that time is extended. This is this case, and this here it is that time is not extended, and this is here. Yeah. Okay, how is possible in first case to calculate real number of particles? This real number of particles is given but real count rate times time of measurement, and also it is given by number of registered cases, and also this was loosed. This is number of registered cases times registered events times that time. It is time in which this detector was not possible for measurement. And if you will multiply by real count rate, you will obtain these loosed events. That means sum of this measured registered events plus these loosed events together, you will obtain real count rate. From this, it's possible, from this equation, it's possible to obtain this real count rate from measured count rate. This K divided by T, this is real, it is number of registered cases or registered events divided by time of measurement. This is measured count rate. That means from measured count rate, you will obtain the real count rate, and it's possible to obtain how many particles were detected really, yeah, if this dead time will be 0. For a case in which this dead time is extended, it is more problematic. It's necessary to start from distribution of intervals between signal which arrival and probability that it will be. And okay, that means this probability that this time will be longer than this dead time. It is given here, and okay, you will obtain, and from this it's possible to obtain a relation between this registration number and the real count rate by this equation. And if you will put this dependencies here, you see this is real count rate and this is measured count rate. And this is for different dead times. Here is very, very small. That means in this case, it's possible to see if will be the same count rate, this real count rates and measured count rates will be same. In this case, it will be should be here. That means here this difference is very small. This influence of that time is very small. First case in which that time is not extended, is here. And here for that time 5 microseconds. That means it is more than 1 order longer that time. And it's necessary to say that that time, for example, for this semiconductor detectors is approximately a few microseconds. For second, it's clear that it is even worse situation. And it is necessary to say that, okay, if you have a first case, that means the worst situation is that will be any time will be blocked this detector by that time. That means it will be only the same number of events as is possible to give by this dead time. For that time extension, that means that if will be very high count rate, it will be only 1 dead time and only 1 gamma will be detected. That means in this case you have some saturation. That means it will be some stop of increasing, and for any real count rate, you will obtain this saturated value. For this case too, if this dead time is extended, that after some maximum that it will start to decreasing and it will end in the one detection but that means it will be zero counter. This is a very dangerous feature of these detectors for some usage, for some purposes. For example, if you will use such detector which have this dead time extension for detection of neutrons from nuclear reactors, it's sometimes very difficult to distinguish situation that you have very small intensities of these neutrons, and on the other side, it's possible to obtain the same measured count rate for very high intensity of these neutrons. And it is very, very dangerous in the case in which you need to know intensity of neutrons, for example, in the reactor, and to know how looks like this fission reactions in nuclear reactor. Okay, fine. Again, we will, during exercises, we will calculate some examples. Next quantity, this is detection efficiency. This is ratio between number of detected particles and number of particles which are emitted by source. This is absolute efficiency. And it consists of intrinsic two efficiency, intrinsic efficiency and geometrical efficiency acceptance. What is geometrical efficiency? Geometrical efficiency is ratio between a number of particles which are running in the direction of sensitive volume of detector to the number of emitted particles.
Excuse me,